Okay, so here we go, quantifiers, section 1.5. All right, so let's get right to the definition here. So what is a quantifier? There's two different types. And let's see, I'm going to make that a little larger here. Hold on. There we go. Definition. So let P be the statement involving a variable x, right? And let D be a set. So we call P a propositional function, right? Or a predicate with respect to D if for each x in D, P of x is a proposition. Okay. We call D the domain of discourse of P. Okay, so here's the definition. Here's an example. I'm sorry. That is the sort of the definition here. Let P of n be the statement n is an odd integer. Okay, so we have to ask ourselves, well, then P is a propositional function with the domain z plus of positive integers, right? Since for each n inside of the set of all positive integers, P of n is a proposition, i.e., for each n, P of n, for each n inside of z plus, the positive integers, P of n is true or false, but not both. For example, if n is 1, P of 1 is an odd integer is true, but P of 2 is an odd integer, that's false. Okay, so we're going to be dealing with these propositional functions, all right? Let's do another example. So in other words, well, notice in here there's an infinite number, I should mention that, infinite number of propositions that are defined by this statement right here. Let P of n be the statement, n is an odd integer. There's one for each positive integer. Okay, let's look at this example. It says example 1.5.3, explain why the following are propositional functions. Okay. N squared plus 2n is an odd integer, with the domain of discourse being the positive integers. Well, the reason it is that it's either true or false, okay, and it is defined over all the integers. Let's see, x squared minus x minus 6 equals 0, where we want the domain of discourse to be the real numbers. Well, you just plug a real number into the left-hand side, and you're either going to get 0 or not. So that statement is either true or false, okay? The baseball player hit over 300 in 2015, where the domain of discourse is the set of all baseball players. Yes, you could just look at the statistics and see if they hit over, if their batting average is over 300. It's either over 300, could be exactly 300, but over means greater than 300. So for each baseball player, this is either a true or a false statement. Okay, etc., etc., etc. Okay, let's move on. Here's a definition. Okay, so if we're given one of these, right, let this be a propositional function with domain of discourse D, the statement for every x, P of x, okay, that's called the universal quantifying statement, meaning that we're saying that for every x, it means for every x, right? So in other words, for every x, P of x. Okay, so may be written for every x, P of x. The symbol, that symbol right there, is called the universal quantifier. Okay, let's take a look at an example. Consider the universal quantified statement. For every x, x squared is greater than or equal to 0. Okay, where I assume we're taking the the domain of discourse is the real numbers. We're not allowing for complex numbers, matrices in here, just real numbers. Okay, so the statement is true because for every real number x, it is true that if you square the square of x is positive or 0. So this is a universal quantified statement, which would be considered to be true. Okay. Let's see. Okay, here we go. According to definition 1.5 for the universal quantifying statement, right? 1.51 is false. Let's see. Oh, this is the middle of a sentence here. Is false if for at least one x in the domain of discourse, the proposition p of x is false. Okay? So a value x in the domain of discourse that makes p of x false is called a counterexample to the statement. Okay. Okay, let's see. Let's determine this. Determine whether the universal quantifying statement for all x, x squared minus 1 is greater than 0 is true or false. Okay, so here the solution is right here. Okay, so basically we know that, well, I guess this is going to be false, right? Because I can, well, let's see, I can find a counterexample. Can't you take, for example, x equal to 1/2, right? Then if I take x squared, that would be 1/4. And if I subtract 1, that's less than 0. So this is false. I don't know what they come up with here. Oh, they're just taking 1 there. 1 squared minus 1 is actually equal to 0. But anything less than, I guess, in absolute value, I guess, less than or equal to 1 would be a counterexample for this right here. Okay. This is just a little code that would determine whether something is true. Like suppose that P is a propositional function whose domain of discourse is the set D1 through Dn, a finite set. The following pseudocode determines whether for all x, P of x is true or false. So for I equals 1 to n, if this not returns false, then you return true. Okay, so in other words, what you do is you there must be a test in here, a program to test whether not P of D is false. If it returns false, then you return true. All right, and if it turns out that that is always, let's see, then how does that work? So what happens if it returns true? Okay, then you just go back up to the next one and do the next one. I guess that's how loops work. Okay, let's see. Verify the universal quantifying statement here, example 1.58. So we want to verify that for every real number x, if x is greater than 1, then x plus 1 is greater than 1 is true. We would like to verify that. Okay, this is, I think, fairly straightforward. What do I mean? Well, let's think about it. So if you take an x greater than 1, right, then if you add 1 to it, that's also going to be greater than 1, right? Let's see, how do they prescribe this? Let x be a real number who, oh, I see, I guess we have to do it, yeah. Let x be any real number whatsoever, okay? It is true that for any real number x, either x is less than or equal to 1 or x is greater than 1. If x is greater than or equal to 1, okay, I mean if x is less than or equal to 1, the conditional proposition is vacuously true. Okay, that would be because in that case, if we chose an x which was actually didn't satisfy that, then by what we know about the then concept of implication, any false hypothesis implies basically that anything, right? Okay, so it'd be vacuously true. And I guess the point of this sentence is that normally we don't consider those cases. Okay, so now let's consider, suppose that x is greater than 1. Okay, and we're not specifying the value. We're letting x be any number greater than 1. Now we have to ask ourselves, if I take x plus 1, that's bigger than 1, right? If you add a positive number to both sides of an inequality, or at least to one side of an inequality, it certainly gets larger. Okay, and you can read through this, and that verifies that statement is true. Okay, here's another quantifier. Okay, here's another definition. So let P be a propositional function with domain of discourse D. The statement there exists x, P of x. Okay, that means the existence of one. And here we use the symbol right there. There exists. Okay, so here it is. There exists an x, P of x, may be written there exists an x, P of x. Okay, the symbol That symbol right there is called the existential quantifier. Okay, so let's take a look at this example. Consider the existential quantified statement. There exists an x, and normally I'd throw a such that. There exists an x such that x over x divided by x squared plus 1 is equal to 2/5. So in this situation, we need to basically find an x where we're assuming the domain of discourse are the real numbers. We're going to find an x that satisfies that. And I don't know, here they just observe that if you put a 2 in there, then then that becomes 2 divided by 5. And lo and behold, that's true. Okay? So, and then they make a point in this next thing, I guess, that it is not the case that every value of x is true. Obviously, if you take 1 divided by 1 squared plus 1, that's a false statement. So, all right, let's take a look at another example. Verify the existential quantifying statement. There exists an x which is an element of the real numbers such that 1 divided by x squared plus 1 is greater than 1. We want to show that that is false. Okay, so we want to show it's false. So we must show that this is false for every real number x, okay? So now we got to think about how we would do that. Okay, so now, well, I'm looking at this and I kind of see what's happening, right? You see, in my mind, without writing it out like this, I'm realizing that if you take 1 and if you divide that by 1 plus some number, then the denominator is going to be larger than the numerator and positive since they're squaring. So basically, for every real number, we're getting 1 divided by some number larger than 1. Well, that's actually less than or equal to 1. Okay, the best case scenario would be if x is 0, right? So that proves that this statement is false. There does not exist, right? There does not exist a real number where this is true. Okay. Right. Okay, let's see another example. Oh, here's a good example. Consider the existential quantifying statement. For some n, if n is prime, then n plus 1, n plus 2, n plus 3, and n plus 4 are not prime. Okay, so this is an existential quantifying statement. For some, I could rephrase this as saying, there exists an n with n prime, okay, such that n plus 1, n plus 2, n plus 3, and n plus 4 are not prime. Okay, so actually, I think the domain of discourse, I wouldn't even consider it to be the positive real numbers. I would consider it to be the prime numbers, right? Because they are saying for some n, if n is prime. I guess we would have to check that, but that's a fine point. Here we go. So here's our example. It turns out if you look through the numbers, right, you can find n equals 23. And if you calculate 24, 25, 26, and 27, all 4 of these are not prime. So that is an example. Okay, there's this generalization of De Morgan's law for logic, which applies to these existential quantifiers. Let's just look at them and see what we have here. The first one is, if I write down, it is not for every x, p of x. That's equivalent to there exists an x where not p of x. And similarly, the other way around. There exists an x means that for every x, not p of x. Okay? So, yeah, just sort of look through those. And you want to get used to that, that notation. And I've assigned a few examples at the end. And I would read through this, but some of it gets this a little detailed. So I'll just leave it out for now. But yeah, so these are the, essentially it's all the same stuff. And the examples that I've given you will lead you to the conclusion. So, okay, that'll lead you to understanding the basic ideas that we need for the rest of the class. So, okay, there's some assignments, and if you need to come back to the video and, look at it, that would be great. And otherwise, you can read the text. So, okay, well, thank you. Hopefully that helps.